Welcome to this explainer. Today, we're going to completely dismantle your geocentric assumptions about the night sky. You know, if you've ever looked up and felt this profound, universal connection to the cosmos, you are definitely not alone. We kind of just naturally assume the sky above us is this shared, uniform canvas. But as we're about to see, the way you experience the celestial bodies above is entirely unique to the exact, literal spot where your feet are planted right now. Which brings us to a really fun, fundamental question. Does the moon actually look the same to everyone? I mean, we all look up at the exact same rocky sphere orbiting our planet. But if you've ever assumed that the lunar view from your backyard is perfectly identical to someone else's view halfway across the globe, well, prepare for a major perspective shift. It turns out our earthly vantage point plays some pretty incredible tricks on our eyes. All right, let's dive right into this. The absolute golden rule we need to establish from the jump is this. Timing is universal, but appearance is local. Think of it like this. When a full moon or a new moon happens, that astronomical event is universal. The clock is locked in for the whole planet. But how that specific phase visually presents itself to your eyes, that is a strictly localized phenomenon, dictated entirely by your coordinates. Let's start with our first major illusion in a section we'll call the Great Hemispheric Flip. Now, what's really fascinating here is how crossing the planet's equator literally throws you into a reversed visual reality. Picture a waxing crescent moon, you know, that iconic thin sliver of light just starting to grow. Someone standing in a northern hemisphere forest sees that illuminated sliver clearly hanging out on the right side of the moon. But at that exact same moment, an observer on a beach down in the southern hemisphere sees it distinctly on the left. It is a perfect, undeniable mirror image. Let's move on and see how this builds for the waxing gibbous phase. The exact same mirror effect happens. Observers up in the north are tracking the light expanding on the right, while folks in the south are watching it take over the left side. They're looking at the exact same lunar phase, at the exact same time, separated purely by geography, which forces a completely opposite visual experience. It's wild. And this brilliantly illustrates what happens as the moon wanes, or starts to shrink. The whole pattern completely flips. Entering the waning phases means the northern hemisphere now sees the remaining light clinging to the left side. Meanwhile, down in the southern hemisphere, they see that remaining light on the right. It's this continuous, perfectly synchronized dance of opposites through the entire lunar cycle. So what's the big takeaway here? The absolutely crucial point is that this left and right reversal isn't some optical illusion happening out in deep space. It's simply the natural geometric result of the opposite physical perspectives of observers standing in different hemispheres. Because the Earth is a globe, standing in opposite hemispheres means you're essentially looking at the exact same object from an upside-down vantage point relative to one another. Moving right along, let's get into our next section, mapping the lunar heights. Because our localized experience doesn't just stop at left and right. Oh no, it's also all about altitude. Your specific latitude and the current season completely dictate how high or low the moon hangs in your sky. Before we crunch the actual altitude data, we have to anchor ourselves with the solstices and equinoxes. These seasonal milestones are the secret keys to unlocking the moon's high and low altitude dance. We usually associate these markers just with the sun, right? But the moon's path is intrinsically tied to these exact same seasonal rhythms. Let's break down this beautifully structured data matrix for the northern hemisphere. It's like a giant puzzle clicking into place. A new moon hangs at its absolute highest during the summer solstice, but hits its lowest point during the winter solstice. But check out the full moon. It does the exact opposite. A full moon reaches its absolute peak altitude during the winter solstice and sits lowest during the summer. And perfectly nestled right in between, the first and last quarter moons hit their extreme highs and lows during the spring and autumn equinoxes. It's an incredibly predictable clockwork system. And just to add one final mind-bending twist to the whole shebang, if you were to travel to the southern hemisphere, every single one of those seasonal altitude highs and lows completely flips in the exact opposite direction. A full moon that beautifully dominates the high winter sky in the north is going to be hanging remarkably low during that same season in the south. Your latitude quite literally rewrites the script of the night sky. Because our view of the universe is inherently biased by where our feet are currently planted on Earth, we start to realize that the cosmos isn't just something we observe objectively, it's something we experience relative to our place in the world. Knowing that the moon's face and its path through the stars are uniquely painted for your specific latitude and hemisphere, you've really got to ask yourself, what hidden, completely different version of the moon will you see on your next global journey? Next time you travel, don't just look around. Make sure you look up.